So I just wanted to start by talking about how I got into ray tracing and why I want to give this presentation. So I first started last April, and at first it was just a way to procrastinate studying for finals. And I didn't really have any specific plans or following any tutorials. And after a few weeks, I was able to make these renders of a person and a cat. And you can tell that they're 3D renders, but they didn't take advantage of any of the benefits that ray tracing gave. So pretty soon after I made these, I found some resources that were way better. And over the course of that summer and winter break, I worked on it basically starting completely from scratch. And most recently, I've made these renders of a metallic statue and a sort of plastic ball. And not only are these a higher resolution and higher quality, they're more complicated materials. And so the goal of this workshop is to basically skip that first few weeks where I didn't know what I was doing and condense the jumpstart of the next period I had into an hour. This code base should be flexible and be easy to add new features if you want to. And this image here will be the final image that the code can generate. So the next thing I want to go over is just briefly the main two ways that you can turn a three-dimensional scene into a two-dimensional image. So the first way is through what's called rasterization, where essentially you start with some shape, whether it's a sphere or a triangle, and you ask the computer which pixels should show this. And it's really fast, but it's hard to get realistic looking light behavior. And so this is traditionally used in cartoon styled games. And this is not the focus of the workshop. But if this is something you're interested in, I would still recommend sticking around because a lot of the same ideas carry over. So the next one is ray tracing, which obviously is the focus of this workshop. Essentially, you ask the opposite question. You start with some pixel and you ask the computer, which object should this pixel show? And it's slower, but it's a lot more realistic because you're literally simulating how the light behaves and how it interacts with the objects in the scene. And what I really like about it is it involves the study of a lot of different fields because you have physics with how light behaves with different materials. You have math because one of the ways to reduce noise is through efficient sampling. And you also have computer science through the use of acceleration structures, where you put the objects in a scene into a tree structure to reduce the computation necessary to find what object array hits. And most of these are beyond the scope of this workshop just for the sake of time. But if any of these sound interesting to you, I'd be more than happy to send you some links after this. So for the new people that joined, there's a link at the bottom of the slides to the repository. And if you want to follow along, I'd recommend cloning that and following the instructions to get set up. So the repository has some provided code just for the sake of time. And so I want to briefly go over those before we start using those to write new code. The first is just a very standard vector3 library that has a tuple of 3 numbers, and it supports the standard vector operations like addition and scalar multiplication. And it contains stuff like dot product, cross product, getting the length of a vector, getting a unit vector, and things like that. So we use this vector class to represent points and vectors in 3D space, but also colors. And we'll see more about that later on. Building off the vector class, we also have array class, which we need for ray tracing. And that stores the origin of the ray and the direction of the ray. And then it has an additional method to find the points at a certain distance along the ray in the given direction. Next, we have a basic image wrapper class that takes care of everything involving writing to pixels to an image and saving the final image.
That's incredible.
So the constructor takes the name of an image as well as its size. It has a method to save it,
I mean, it was like a
and
really,
it has a method to write a
well, I
given
think some
color
context
pixel
to that,
to the
like
given
the
pixel
native language was
coordinates.
literally just you add a D in front of it.
Sounds like someone here isn't
Hey,
muted, so unless you have
Tim,
a
can you
question,
mute?
yeah, please mute yourself. Thanks. And lastly, we have a camera, which a camera is actually pretty interesting and how you want to abstract it into something like this. But the way we're going to do it is that a camera can be thought of as a point in three-dimensional space with a viewing direction. And so in that viewing direction, there's an imaginary two-dimensional plane. And that plane is what the three-dimensional scene is projected onto, giving the final image. And so you also need to provide an orientation because you can imagine you're able to rotate the camera along that axis and get a different picture. And so the constructor for the camera will take the location of the camera, view direction. In this case, we actually specify our target because it's easier to say, I want to look at this object instead of I want to look in this direction, as well as an orientation, which is passed as a vector that should be up relative to the camera. The last thing that a camera has is the field of view, which you might be familiar with from settings in video games. But essentially, it's the field of view, which is theta in this diagram, controls the zoom of the image. So if you increase theta, then the height of the imaginary plane increases. And so you capture more of the scene. So which means that the higher field of view is more zoomed out, which might be a little unintuitive. And this just shows explicitly what the constructor is and what its parameters are. And then it also has an additional method called generate ray that takes an XY pair, both between 0 and 1, and returns a ray that starts at the camera and goes through that point in the plane. So if you pass 0, 0, it would return the ray through the bottom left corner, and 1, 1 would be the ray through the top right corner. And with that, we can finally start writing new code. So let me know if what I type here is too small. I've tried to zoom in, but I can all still zoom in more if it's still a little too small. So I'm going to start by importing the vector3, the ray, image wrapper, and camera, all the classes we need from the library. Let me just double check. So it's lib. And then we're going to have a main function that basically has all the data. So we're gonna I just chose for this to have the aspect ratio be 1, so it's a square image with a height of 256 pixels. And then we can calculate the width as height times the aspect ratio. And although in this case, we don't need the cast to int, it's necessary in general if aspect ratio isn't an integer. And then we can call some name for the output image, like test.png, and use this to create an image wrapper with a given name, width, and height. Now for the camera, we can choose basically to orient it however we want. I chose to have it positioned at the origin, which means a vector 3 at 0, 0, 0, pointing along the positive y-axis, which is 0, 1, 0, and having the z-axis be up, which is 0, 0, 1. And then the aspect ratio we defined earlier, and a vertical field of view of 90 degrees. And so afterwards, you can play with changing this number and see how it affects the final scene. The next part is the main render loop. So we want to iterate through each row in the image, and then for each pixel in that row. And then we want to generate the ray going through that pixel. So we have the camera.generateRay method, but that takes numbers between 0 and 1. So we just have to divide x by the width and y by the height to get the correct ray. And then we do some sort of operation here to get the color of what that pixel should be. But once we have it, we can do wrapper.writePixel at x, y, and the given color. And then when we're done, we can save. So is there any questions up to this point? Yeah. So just before we try to do anything complicated with geometry or trying to render an actual shape, I like to start with just a basic gradient that will make depending on the angle or the z component of the ray's direction. So normally colors are stored as integers from 0 to 255, but as we'll see later on, when we're doing operations on colors, it's often useful to instead have them be floating point numbers between 0 and 1, in which case the color white would be 111, and the color light blue would be 0.5, 0.71. And the wrapper.writePixel method takes care of that for you, of converting it to the correct value to save to the final image. So essentially what we want to do is get a number between 0 and 1 based on the z component of the vector's direction. So if we do ray.direction.normalize, that guarantees that each of the components is between -1 and 1. If we add 1 to this, it's a guarantee that this is between 0 and 2. So if we take this and divide it by 2, this gives us a value t that'll be between 0 and 1. And then with this, we can do t times blue plus 1 minus t times white. And this is linear interpolation. So if t is 0, then this term goes away and we're just left with white. Alternatively, if t is 1, then this term goes away and we're just left with blue. So we can run this, hopefully not get any errors, and that should have made a, hold on. Give me a second. That should create, so it should look like this, but for some reason I'm not seeing the final picture show up on the side. Let's try to name it using a different name. All right. I'll keep going through the workshop because all the pictures that should generate are in the slides. But if anyone sees why that image might not be showing up, let me know in the chat. But once we have this and we know that we can write to an image correctly, the next step is to actually add some geometric objects to the scene and do some intersections with that. And so the geometric object that's usually first used is a sphere ray intersection. Now this is a little math heavy, and so if that's not your thing, you can just sort of focus on the end result. But if you're interested in the derivation and seeing that what we're doing is true, you can look through the slides and details after the workshop to verify it. But essentially, the question we have is, given array with an origin O and direction D, where does it first intersect a sphere with center C and radius R? And we can simplify this question slightly because we can translate both the ray and the sphere by the same amount until the sphere is centered at the origin. And so we have an equivalent question where the ray is centered at O minus C with the direction D, and the sphere is centered at the origin with radius R. And then using the parametrization of the ray and the equation of a sphere where the point is on the sphere, if it satisfies p squared equals r squared, we end up with this equation that we want to solve for t. And so this slide has all the derivations if you want to look through it on your own. But essentially, the important part is that we end up with a quadratic equation in t, with the a, b, and c, the coefficients in the quadratic equation, given by these formulas based on the dot product.
Hey, Calvin, just to butt in really quick, I think somebody might have found the issue. They said in the Git repo, you have wrapper.save on a different indentation. And so I think if you move like line 18 in a bit, I was running the code myself, and I think that it was working. It just doesn't actually save the file until it's completely written. Whereas if you indent it, it looks like you can actually see it being saved in real time.
It actually wasn't calling main. That was the problem.
That could do it too.
All right, there we go. And so yeah, it showed up. So the code I have is right. Yeah. So the next thing we want to do is figure out, given the solutions to the quadratic equation, how can we interpret that geometrically? So if we have two real solutions, then the ray intersects with the sphere twice. If both solutions are positive, then both intersections are in front of the ray, which is this first sphere here. And we want the solution at t0. If one is positive and one is negative, that means the ray starts within the sphere, as in this third sphere, and we only want T1. Because remember, a ray is like half of an infinite line. We don't care what happens behind it. All we care about is what's in the direction of the direction vector relative to the origin. So if both of the solutions are negative, then the sphere is completely behind the ray, as in this rightmost example, and we say there's no intersection with the ray. Alternatively, if there's exactly one solution, then the ray grazes the sphere or is tangent to it, and we get this case in the second sphere. We can take either T0 or T1. Finally, if there's no real solution, then the ray just completely misses it and there's no intersection. So to code this up, we first need a method that solves the quadratic equation. And this method is just really a standard implementation of that. It's called solve quadratic, taking in coefficients a, b, and c. So the first thing we have to do is calculate the value under the square root, because that determines the number of solutions. So if this is less than 0, then there's no real solutions, and we can just return an empty list. If it's exactly equal to 0, then there's exactly one solution, and you can calculate that it's negative b over 2a. And finally, we have two solutions, and we need to explicitly calculate them. So we have to calculate the square root of the term under the square root. And then the two solutions are negative b minus the square root of that all over 2 times a, or b plus, which is negative b plus all over 2a. And for the sake of convention, we want to always return the smaller solution first, because when we're looking through these later on, all we want is the smallest positive intersections. So the sooner we can get to that, the better. So we can just return the min of b minus and b plus, and then the max of b minus and b plus. So then with this, we can use that to make a sphere intersection method. So that'll take the center of the sphere, the radius of the sphere, and the ray object. And this basically involves calculating these 3 coefficients here. So the coefficient A is ray dot direction dot ray dot direction. B is 2 times ray dot direction dot ray dot origin minus center, and C equals ray dot origin minus center dot ray dot origin minus center minus radius squared. So then we can pass those coefficients and just solve quadratic, and we'll get a list of solutions back. So we can iterate through those, and if we have a positive solution, that means that the ray intersects with the sphere in front of the origin of the ray, which is exactly what we want. So we can just return true. Otherwise, if we get through all of them and they're all negative, or there are no solutions, we can just return false. And so back in main, we can define a sphere. So we'll have it center at 0, 10, 0. So that's in the viewing direction with a radius of 5. And if there isn't an intersection between that center, that radius, and the ray we generate, whoops, gotta move that up here. So if there isn't intersection, then we can just set the color to just a bright red color. Otherwise, we can do that same thing as before to get that background blue to white gradient. So if we run this, it ran, and we get this image with a red circle in the beginning, which is exactly what we want. So before we move on, next step is to sort of just abstract this into a sphere class, just to make it easy to define multiple spheres. So the constructor will take the center and radius, as well as the color. And I need self here. And we just need to save those variables. And then this intersection method will become a method that belongs to the sphere class. So we can get rid of the center and radius parameters and add self. And then when we want to access those, we just have to add self dot in the front. So self dot center, self dot center, self dot radius, self dot radius. Now the only thing here is that now we can't just return true or false. We would have to return like a tuple, true, and then self dot color, or false and self dot color. Alternatively, you could just return self dot color here and none here, the Python none object. But right now, the only information we would want to return is the color. But if you imagine a more robust renderer, it might have to store texture coordinates, texture information, information about the material itself. And so what a lot of renderers do is make a class whose only purpose is to just store all that together, store all the local information relevant to an intersection between array and some geometric object. So that's what we'll do first, is make a class called hitRecord that stores the points of intersection in three-dimensional space, the color of that material, and the time along the ray. So, and it doesn't have any additional methods. It's literally just a class that keeps all the information linked together. So now here, instead of just returning true and self.color, we want to calculate the points of intersection. And we can do that because the ray has an at method that will return the points at a given distance along the ray or a given time along the ray. And since we found that in the solution, we can just do that directly. So now we're just going to return a hit record with the points, the color, and the time, which is solution. And if there's no intersection, we just return none. So if we run this, it should still work. Oh, we just need to rename this to intersection. So we have to make this a sphere instead. So center radius. So let's do that. And then record equals sphere.intersection with the ray. And then if record is not none, so if the record exists, then we can set the color to the color in the record. Otherwise, we can do the same thing as before, take the background. Oh, I forgot a self dot right there. And that gives the same picture, which is exactly what we want. So the next step that we want to do is allow to intersect with multiple spheres along the same ray and figure out which intersection comes first. So let's make a method down here called getIntersection with a given ray and a list of spheres. And this will return the color associated with an intersection, if any. So to do this, we need a variable to keep track with the closest intersection along the ray. And we'll initialize it to some absurdly big number, like 10 to the 100. And found record will hold the hit record associated with the intersection at this time. And then for sphere in spheres, we get the record using the intersection method with the ray. And if the record is none, then we can just continue because it doesn't matter. But if the record does exist, and if the time along the ray of this intersection is less than the nearest that we found so far, Then we can update the found record to hold record and update nearest to hold record.time. So this will update so that we always keep track of the closest intersection through all the spheres so far. And at the very end, if found record is still none, then no intersection, and we can just do the same gradient from earlier. So let's actually move this into a separate class or a separate function. So def get background for a given ray. So it'll just compute the t parameter based on the ray's direction and then return the linear interpolation. Was there a question?
I don't think so. I think somebody might have just accidentally unmuted.
Yeah, that's fine. So at the end, if there's no intersection, then we can just return get background for the given ray. Otherwise, we want to return the color associated with the found record. So now let's do this. We can get rid of most of this. So let's define a red sphere up here, which is just this same stuff. Actually, let's make it all together. So we have the same center, 0, 10, 0, radius of 5, and a color of 1, 0, 0. And then we'll make an additional green sphere, which will be at 0, 10, negative 100. So this will be directly below the red sphere with a radius of 95, so that the two should ideally like touch each other at a single point. And then we can make a list of spheres containing the two. And now instead of all this junk, this is all taken care of up in the get intersection method. So we can do color equals get intersection with the ray and with the spheres. So let's run this, see if I made any typos. Yeah, so we need to move blue and white into here as well. Give it a second to run. And now we have two spheres, just as we want. And so the thing you'll probably obviously notice is that this is just a two-dimensional picture. There's nothing to suggest that this is supposed to be a three-dimensional scene. And the reason for that is right now, the rays that we send out from the camera stop once they hit something, which isn't very realistic. You know, in real life, light bounces around until it's absorbed by something. Now, technically, we're doing the process in reverse. So we're starting with a ray at the camera and bouncing around until we hit a light source, instead of having the lights or rays start at light sources and stop once they hit the camera. But the same idea still applies. We want to be able to make the rays hit the red sphere and then do some calculation to figure out which way it should bounce towards, and do that over and over again to get a more realistic shading in shadows. And really, the only thing you need to define a material is defining that function of how a ray bounces off of a material. So the easiest material to simulate is called Lambertian, and it's supposed to model rough surfaces and look the same from all angles. So you can imagine like a shirt that's laid out or a rough paint. You know, there's no highlights, no matter how you angle the light or how you look at it. And this is done by having it by generating an arbitrary unit vector, so that the output direction, all output directions are equally likely. And so to do this, we need a function to return a random unit vector. So let's go up here. First, we need to import random, and then rand on sphere. So the easiest way to do this is to generate a vector in the unit box and then normalize it to make it a unit vector. The only tricky thing is that random.random returns 0 to 1. So we just have to do a slight modification to get it in the range from -1 to +1. So V is in the unit box, and then we return v.normalize, which is guaranteed to be in the unit sphere. So the other thing we need is the normal of a geometric object, because that's sort of the symmetry point. That's what it's bounced relative to. If you're taking calculus, you might be familiar with the normal vector as being perpendicular to the surface. And for the sphere, it just so happens that the normal vector is just the vector from the center to the point. Because you can imagine if we take this vector OP and continue extending it outward, it's going to be perpendicular to the surface of the sphere at P. And so we can calculate it just as P minus self.center dot normalize. Then once we have this, we'll have the normal vector n, then a randomly generated unit vector d. The new direction that the ray will travel in is just the vector addition of them, n plus d. And so every point on the surface of this unit sphere will be equally likely to be picked. And that's what generates the Lambertian surface. Now, the last thing we need to do is update the hit record to store the normal vector. So that just involves adding another parameter to the constructor and then calculating it here. So the normal is P minus self.center.normalize and add that here. So then the other thing we need to do is figure out how to actually combine rays together after they bounce. Because really what we're doing is the same thing over and over again. With the first call, we have a list of spheres in a ray, and we want to get the color associated with that ray. But once it bounces and we send it in a due direction, we want to do the same thing again. And so what we want to do is make this get intersection function recursive. Just keep calling it over and over in a loop until we bounce so many times or hit a light source, and then travel back up the recursive stack until we can finally calculate the final color of that pixel or associated with that ray. And so we need to have another parameter, depth, to keep track of how many bounces we've done. Because you can imagine if we have a scene consisting of two parallel plates, a ray could get stuck bouncing between the two infinitely many times, and the render would just get stuck. So we just hard code an upper limit of how many times it can bounce. And we'll have the convention so that the initial call has it as a high number, and we subtract 1 with each call until we end up at 0. So if depth is 0, then we can just return the color black and say that vector doesn't contribute anything. Otherwise, this is where we have to figure out what to do. So the new direction is the found record dot normal plus a random vector on the unit sphere. And then the new ray, it's the ray that starts at found record.p and has the given direction. And then the new color associated with that new ray is the result of the call to get intersection with the new ray, the same spheres, and depth -1. And then the next thing we need to do is figure out how to combine new color with the color of the current intersection. And it should hopefully make sense that we want to do is component-wise multiplication. Because if new color is white, so if we bounce off something that's completely white, then it shouldn't affect the color of other things that same ray has hit. Alternatively, if new color is black, that should just get rid of any chance, that should just get rid of any color that ray might already have had on it. And so we want to do that multiply new color. And so this is exactly why we have colors be between 0 and 1, not between 0 and 255. Because if you multiply white with white, and they're both from 0 to 255, you would end up with something that goes up to like 65,000, which is way out of the range. This allows us to just multiply them component-wise and just be done with it. So if we run this, got to update the call. So we'll say with 20 bounces, hit record, ellipse.point. So one thing you'll notice is that this is immediately taking significantly longer to finish. And that's just the nature of ray tracing, where bouncing the ray multiple times is just going to cause the render time to increase. But the other thing you'll obviously notice is that this is really noisy. And this is because a single ray can't capture enough information to accurately estimate what the image should look like. So if you imagine a ray coming in and hitting with the red sphere here, it might reflect off and bounce down and hit the green sphere down here, or it might bounce up and go off towards the sky. And both of those would result in very different pixel colors. So there are some advanced techniques you can do to reduce the noise, but the easiest way is just to sacrifice time at the cost of accuracy and just send out multiple rays per pixel and take the average of them. So that will involve choosing a random number. So let's say samples equals 50. So we send out 50 rays for each pixel and take the average color. So for each sample, generate a ray, generate the color, and then we want to have a final color starting at black, keep track of the color we've accumulated, and increment final color with color. And then at the end of all the samples, we divide final color by the number of samples to get the average, and we write this average instead of any one single sample. Now I'll also indent this so that we save the picture at the end of every row instead of when we're done. Because as you'll see, this now takes a lot longer to run, 50 times longer. But I'll let this run in the background. But as you'll see in the slide, this does significantly impact the quality. So there's obviously still noise in that you can see it's not a smooth gradient from bright to dark on either the green sphere or the red sphere, but it's a lot better than it was here. And there's not really much you can do about that other than either sending more rays per pixel or getting into those advanced techniques that require heavy math or computer science to fully understand and that are beyond the scope of this workshop. But one thing we can do to at least improve the quality, if not the noise, is if we zoom in on the boundary between the red sphere and the sky, it's just a harsh boundary. There's no smooth gradients. That's because each pixel only contains what's at the center of the pixel. So if you can imagine, if we have the grid of pixels with the blue sphere and the red sphere, with what we have now, it would color each pixel wholly with what color is at the center of the pixel, which would result in these harsh blocky shapes. And this is actually pretty easy to fix. What you just do is nudge each original ray slightly, and so that instead of sending each ray through the center of the pixel, they go through a random part of the pixel and let it average out. So I'll stop this and add the anti-aliasing through here. So the offset x will just be the x plus random.random. So that's random.random returns a number between 0 and 1. So that'll return a ray between the current pixel and the next pixel in each direction. And then if we use OX and OY, let that run, what we'll see is that for most of the picture, it doesn't do anything. But when we have the boundaries between the red sphere in the sky or the green sphere in the sky, you can see it really make a difference, especially if you zoom in. So now we have this nice smooth gradient from the red sphere to the sky. So pretty much the last thing I want to do is abstract the Lambertian material into its own class so that you could potentially use that to make other materials if you wanted to on your own. So basically the only method a material has to have is a scatter, which will return the direction for a new ray. So let's put it right here under the sphere. So class Lambertian. Ignore that. So the only thing the material has to keep track of is its color. And then it obviously has the scatter method. which will take the hit record and the ray. And in this case, rand on sphere. In this case, we don't use the ray parameter because Lambertian bounces in the same direction regardless of the input vector. But for different materials, you will use the ray parameter. And so you want them all to have the same function signature. So that's just for consistency if you want to add more. So now we have to update the sphere to, instead of having a color, have a material. Oh, that's hit record. So this is material, material, material. And same with here. So we want to place basically all references to color with material instead. And then in here, in get intersection, this would be found color dot material dot color dot multiply new color. And then the last thing to do is update the render loop with replacing the color with the material. So now instead of red, it's a Lambertian red or Lambertian green. So this workshop code. So this should give the same output image, but again, this allows you to have this class that lets you add other classes, like for a metallic material or a glass-like material that you can easily combine together. Now this is what the final scene looks like at 5,000 samples per pixel, which would take about 2 hours to finish, I think. And so this is a pretty high quality image, I think. So the last few slides I have are links to resources and also a small list of suggested improvements or additions you can make to this. The first most I would recommend doing is implementing a reflective metallic material, which is its scatter method would just involve reflecting the ray about the normal, which has a formula you can look up. Additionally, you could implement a transparent glass-like material where you refract the ray using Snell's law. Another thing you can do is go into lib.py and modify the camera constructor and use this focal length to create depth of field, where objects that are closer than the depth or further away are blurry, and only the objects that are the correct distance away are in focus. Additionally, you could add texture coordinates so that you can wrap an image on a sphere. That's what I did here with the cat. I also would recommend adding support for more shapes, especially triangles, because once you can do a ray triangle intersection, you can import arbitrary meshes, and then you can just basically render anything. 3D rendering is also a really good project if you want to get into multi-threading, because rendering is embarrassingly parallelizable. Because basically you can have a single threaded part at the start where you set up all the materials and objects, and then once all that data is written, that data won't be modified, and so you can have multiple threads read it at the same time without having to worry about synchronicity issues. The only problem with that is merging the data that the multiple threads find into a single final image, but I think it's a fun challenge. And it also highly benefits from additional threads. So for example, if you make this 6 threads instead of 1, it will run like 6 times faster, up to basically as many threads as you can throw at it. All right, so finally, this is some lists of resources that I would recommend looking at if you want to learn more. Ray tracing in a weekend. My slides in this project is heavily based by the series. It's written in C++, but if you look at it, you can see that my code is almost an exact match to what they have. And so it's easy to jump start from where we left off here and continue on with ray tracing in a weekend. Physically based rendering is another amazing book. It won, I think it was an Academy Award or something, because it was that good at helping movie studios improve their CGI. It's really in depth and math heavy, but it's what I used to get it's what I used to generate these two. I couldn't recommend physically based rendering enough. Another one is advanced global illumination, which is also very math heavy. A link to a variety of materials that you could implement. There's also a link to a Discord server about 3D graphics. I can type that in chat if you want to join. They have channels for software rasterization rather. Basically anything you could want to do with computer graphics, they have a channel for that and people you could discuss with for that. And finally, there's a list of 3 websites with meshes that you could use to download and render. That's where I got like these meshes or the statue here. But that's all I have for now. Let me know if you have any questions. I can also put my Discord in the chat if you want to ask me some questions there. Let me find where I can see. I don't remember offhand. Let me double check.
I don't have any questions personally, Calvin, but thank you so much for such an in-depth workshop. That was super fascinating. And I'm surprised that you were able to cover so much information so well in only